In this video, we are going to talk about how to perform a multi-discipline optimization with Nastran Solution 200. This video is also going to cover how to handle scenarios where you have multiple subcases. If you're performing, say, a static analysis, you might have 100 or 1,000 load cases that you want to optimize for. I'll cover that in this tutorial. And before getting started, my name is Christian, and I will be going through today's tutorial. We are going to work with a very similar example we've done in the past, the 3-bar truss example, and you'll find this in the optimizations user's guide. For the most part, the optimization problem statement is the same. We're varying the 3 cross-sectional areas for these 3 members. We want to minimize the weight. We're going to optimize for both stress and displacement. Now, this example will be multidiscipline because we are optimizing both for static analysis, that's where our stress and displacement constraints come from, but we are also optimizing for natural frequency. So this involves a second analysis discipline known as normal modes analysis, or eigenvalue analysis. So here we want to make sure that the first natural frequency is greater than 80 hertz. Number 2, this example will have, I believe, 10 load cases. So I'm going to walk you on how do you assign your constraints to different subcases or load cases. And just a quick reminder, if you're an engineer and you have questions, you have comments, you want to work on a project of your own and you want guidance, you can send me an email at this email address and I will get back to you with a good reply. If you're a student or engineer and you want access to the web app we are using in today's tutorial, you can also contact me with your requests. Now, before starting, let's go ahead and download the starting files. If you open the web app and go to the user's guide and go to the size optimization tutorials, you'll find this example called optimization for multiple load cases or subcases. If you click on the starting PDF files, this will download a new zip file. These are the files that we need in order to start this example. So what I'll go ahead and do is I'll just extract the contents here on my desktop. Now let me move a set of files to the right. Now these first 2 files, model BDF and design model BDF, this is from the previous example where we optimized for just static analysis, where we optimized for stress and displacement constraints. I've already gone ahead and set up this problem, so you see it's already solution 200. It already has design variables. It already has the constraints for stress and displacement. Now, this third file, DSOUG1 modes, this is the same 3-bar truss, but this is configured to perform a solution 103 or normal modes analysis. All the same materials, the same structure, the same nodes, that's the same in this file. What we need to do now is perform a conversion process, or rather a merging process. So what I'll do is I'll open the modes PDF file on the left, and on the right I'll open the static optimization file. So that will be here on the right. If you look carefully at this first subcase, you see that the current optimization analysis is set to static. So all of these load cases, and here you can see there are multiple load cases, up to 20. These will all be optimized for a static analysis. Now, if you want to perform a normal modes analysis, we need to take entries from the left file and move them to the right. So the first thing you should move over is the subcase. So we'll go ahead and cut that out and we'll paste that here on the right. Now, keep in mind that this subcase has pointers. It's pointing to a method 1. This one is pointing to the eigenvalue extraction method entry. So that'll be this row. SPC 100, it's pointing to the constraint entry that's defining how the nodes are constrained. These next 2 entries are defining what quantities to extract for the analysis. So we need to make sure that the necessary method 1 and 100 entries are available in this other file. So first, let's go make sure that the method 1 pointer is pointing to the eigenvalue extraction method. So here, let me go ahead and just cut that and move it to the bulk data section here on the right. So here, I'll just go ahead and paste that here. So now this method 1 is pointing to this eigenvalue extraction method that you see here. And here the ID is 1. Now SPC 100, since this is the same structural model, you'll find out that there's already the identical SPC1 entry here with an identification number of 100. So perfect, we don't have to move this over. It's already in the model. I'll close the file on the left, and that concludes the merging of this mode and analysis subcase. So now we'll go ahead and save this file, and we can delete, we can ignore this modes file, so we can delete it if we want to. This is our starting point. We are going to load this set of data to the web app. And the first thing we are going to do is review our optimization problem statement. Let's make sure that the design variables have been imported. Here I see design variables 1, 2, and 3. Let's make sure that we're minimizing weight, so that came in through properly. And here for the constraints, we have our displacement and stress constraint that have been defined for the static load cases. We need to define our third constraint for the first natural frequency. So for this, let's go up and we'll change the analysis type to normal modes. And here we'll click on the plus icon for frequency. This is where we can say constrain the natural frequency for mode 1. And we want to make sure that the natural frequency is greater than 80 hertz. Let me go back to my optimization problem statement and make sure that it's 80 hertz. Yes, it is. So now after you specify this third new constraint, move over to the subcases section. Here, if you click on plus options, you can expand the table. This, if you look carefully, has all of the load cases with the assignments. Here you can see that the displacement and stress constraints have been assigned to load case 1, 2, 3, 4, essentially all of the constraints that you see here. Now, what do we do now? We can deselect some of these checkboxes. So if we want subcase 2 to only consider the displacement constraint, we can mark this checkbox. If we want load case 3 to consider only the stress constraint, we can mark this checkbox, and so on and so on. Now here, what do I want to do for subcase 1? Remember, subcase 1 was the load case that we merged over. It's a normal mode subcase, so we should deselect these checkboxes. Alternatively, I believe if you change this analysis type to normal modes, it removes these constraints. So once we change the analysis type to normal modes, this load case will be optimized for normal modes analysis. Next, let's mark the checkbox for the third natural frequency constraint. So we'll mark that checkbox. Everything looks good. Now we can go to the exporter and download this new set of files. So let's go ahead and do that now. My new package has been downloaded, and I'll go ahead and perform the extraction. I'll go ahead and start the optimization now. So that's how easy it is to optimize for multiple load cases. And if you want to perform multi-discipline optimization, you need to, 1, move over the subcase, and number 2, you need to assign the appropriate constraints to the appropriate subcases. So here, subcase 1 is a normal modes analysis subcase. So then I have to assign it a natural frequency constraint. So here the optimization is complete. You'll see that the run terminated due to hard convergence. It has a green checkbox indicating the optimization has gone through successfully. I see that this example took 7 design cycles to go through. You see that it started at a value of 4.828 and ended at a new weight of 2.69. Here you see my 3 design variables go from 2 and 1 and eventually land on 0.83 and 0.33286. Now let's give some attention to the normalized constraints plot. Here you can see we have our normalized constraint values. You might be asking yourself, what constraint is this exactly? So for this, you need to use a tool under the results section here, responses, mark that open. navigate to the directory where the optimization occurred and upload the F06 file. This is going to give you a list of all the quantities that have been considered for the optimization. And here, click on maximum constraint for each design cycle. And let's go ahead and move this table to the left and move this next plot to the right. So let's start off with this first normalized constraint value, negative 0.07667543. If we look in the table, you can see that value is reported in this column that you see here. It's reported for R3. Remember that R3 corresponds to the natural frequency constraint that we specified. So for the initial design cycle, the natural frequency constraint was, it was dominating, it was controlling the first optimization cycle. It was actually a value of negative 0.0766. So a negative normalized constraint value means that this constraint was being satisfied. It just so happened that it was the closest constraint to being violated. So that's why it's the controlling or dominating constraint. After that, for the first design cycle, you see that R2, which is a stress constraint, is now governing the design, and it now has a normalized constraint value of negative 0.0048. And if you look here at the plot, the second value is negative 0.0048. The next one is negative 0.0166, and that would be this value here, negative 0.0166. Now, what if you want to know specifically which element is causing this? If you click on the blue icon, it gives you more information about specifically what element or node is causing the constraint. So here we see that element 3, the axial stress, item code 2, is causing the constraint. And this is for subcase 3. And here, if we look at the very end, we see that element 3, axial stress, for subcase 3 is still the dominating factor. And here you see the actual value of that stress. It's 20,000 units of stress. So it'd be worth actually showing you that value in Patran. So if I go and I upload the newest result file, this result file, as before, always has both the initial and the optimized parameters. So here, let's go ahead and upload this new XDB file. For you, it might be an OP2 file. And what I'll go ahead and do now, we'll go ahead and look at subcase. What subcase was it? I believe it was subcase 3. So subcase 3, right? So let's go ahead and find that subcase. Load condition. Oh, these are all called the same. SC3. So here you can see we have two subcases here. Subcase 3, the first one, corresponds to D0. That's the initial design. D7 is the design at the last design cycle, which is the optimum structural design. So here, let's go ahead and plot the actual stress results. Let me just go ahead and plot that to see what that looks like. Might be worth increasing the size of this. So there we go. This is the initial design, but what I want to look at is the final stress for element 3. So here, if you look closely, this is element 1, 2, and this is element 3. So this is the element that has the stress value of 20,000 units of stress. This is the same value that's being reported in this last row. Element 3, axial stress. For subcase 3, design cycle 7, it should have a value of 20,000, and that's reported here in the value column. So there you have it. That is how you perform a multi-discipline and multi-load case optimization with Nastran Solution 200. I'll actually walk you through one last step. Let me see if this is worth mentioning. Right, it'd be worth showing you some additional functionality when you're assigning load cases. You might get to the point where you're dealing with hundreds of subcases or load cases. So here I'll take time to give you some more guidance on this large table. So you can individually click these checkboxes. You see the hand icon show up when you can click something. Alternatively, you can hold the shift key and just hover over all of these checkboxes, and you can see I'm deselecting them as I wave the cursor over each checkbox. Another thing you can do, if you want to specify only some subcases, you can use these checkboxes or these buttons here to deselect and select every visible checkbox. So here, if I want to deselect all these checkboxes, and then I want to say, go back here and mark all these checkboxes, you can do that here. And then at the end, if you want, you can select all of these subcases and view what the constraints are assigned to each subcase. So there you have it. This subcase selector, if you will, is a very useful tool when you're performing multi-discipline or multi-load case optimization. I hope you found this tutorial helpful. If you have any questions or comments, if you're a student or engineer and you want access to this web app, you can write me at this email address and I will get back to you with instructions on how to get access. Thank you for watching.